Algebra 2, let's talk about tangents today. So far we've done sine and cosine. And remember, sine sort of has to do with the y coordinate and cosine with the x coordinate. Tangent combines those two, sort of fun. Really something I needed to set the stage a little bit, and I didn't have a creative way to do it, so I'm just giving you 2 vocabulary words that you need to know. So secant to a circle. A secant line to a circle is a line that intersects the circle in exactly 2 points. Circle. Secant. Okay, intersects in 2 points. A tangent to a circle. A tangent line to a circle is a line in the same plane that intersects the circle at only 1 point. It can only be 1 point. It must only be 1 point. Sort of hard to draw on an iPad. Okay, this would be my tangent to a circle, and this is secant. Alright, now let's get into the lesson. First of all, let your point with the ordered pair x theta, y theta be the point where the terminal ray intersects the unit circle after rotation by theta degrees, as shown in the diagram below. Okay, remember, these are just all review. I've got my initial ray, and my terminal ray, and my angle of rotation, which in this case is theta. The point on the unit circle is ordered pair xy. Q is the vertical, it drops down to the x-axis at a right angle. I think that's it. Cool. Let's answer some questions about this. So first of all, using triangle trigonometry, what are the values of x theta and y theta in terms of theta? And this is where we have cosine and sine. So x theta equals cosine of theta degrees, and y theta equals sine of theta degrees. By using triangle trigonometry, what is the value of tangent theta in terms of x and y? Well, tangent, let's rewind a little bit. If you remember, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent, so ka toa. So tangent equals opposite over hypotenuse. But tangent, which is a much more useful way to think about it with a unit circle, is really y theta over x theta, which is opposite over opposite over adjacent. I'm not sure what's going on there. Let's fix that. Sorry. If I look at my theta, opposite is my y value, adjacent is my x value. So if I put it in terms of sine and cosine, which is my terms of theta, I've got sine theta over cosine theta. And we just spent the last 2 lessons talking about sine and cosine, so now wrapping that into tangent won't be too difficult. Here we're just summarizing what we just said in the last slide. If theta is any real number, so we're going to say let theta be any real number, it's our degree of rotation. In the Cartesian plane, rotate the non-negative x-axis by theta degrees about the origin. Intersect the resulting terminal ray. Okay, that's our terminal ray is our angle of rotation, the ray that results from it, with the unit circle to get a point xy. Okay, x theta can't be 0. That means that my terminal ray can't be directly. Okay, this is where x would be 0. That doesn't work for tangent. So x cannot equal 0. Then the value of tangent theta is y theta over x theta. In terms of sine and cosine, tangent theta is sine theta over cosine theta. For cosine, theta cannot be 0 because it's in the denominator. Okay? there's our definition. We just said it again. Said it last slide. It's okay though. Okay, let's do an exercise. For each value of theta in the table below, use the given values of sine theta and cosine theta to approximate tangent theta to 2 decimal places. So we just said that, oh, I'm still in highlighter. Tangent theta degrees equals sine theta over cosine theta. So we're going to do just a little bit of division here. I'm going to push pause and work through them. There's this page. There's another page, which you see on your classwork. I honestly don't need you to do all of this division. It's not necessary. I know that you know how to do division, so I'll move to the next slide. I should point out, though, that if this is my degrees, all of these values were found using the sine function and the cosine function on your calculator. We haven't practiced that yet, but I know you've practiced that in past classes. And then here is where we're just taking sine divided by cosine and getting our answer. Next page. I will point out between the last slide and this slide, there's a pattern. We see this side of the chart and the previous side of the chart. We were all negative to all positive, and it's all repeating. So when our degrees was negative 89.9, our tangent was negative 572.96. So the pattern repeated itself, but went negative. And let's look at why. So as theta approaches negative 90 degrees and theta is greater than negative 90 degrees, what does the value of sine theta approach? If I just look at the chart, sine theta approached negative 1. Okay, and as theta goes to negative 90 and theta is greater than negative 90, what value does cosine theta approach? That approached 0. Okay, if we just look at the chart. So part C, as theta approaches negative 90 degrees and theta is greater than negative 90 degrees, how would you describe the value of tan theta equals sine theta over, I don't know why I wrote that, cosine theta? Well, as tan theta degrees approaches negative infinity. Moving on. Okay, we just did this one. Sorry, I did it on the last page. How about as theta approaches 90 degrees and theta is less than 90, what value does cosine theta approach? Well, it approaches 0 also, if you check out the chart. Sorry, it approached 1. My bad. I looked at the chart backwards. And then as theta approaches 90 and theta is less than 90, what value does cosine theta approach? That one approaches 0. As theta approaches 90 and theta is less than 90, how would you describe the behavior of tan theta, which is equal to sine over cosine? Well, it's opposite of the previous tan question. That one approached negative infinity, this one approaches infinity. And then finally, how can we describe the range of the tangent function? Parentheses, negative infinity to infinity. Notice it's not brackets because we can never include infinity. And this really means, the set of all real numbers. Which I can write as a fancy R. Okay, let's do an example. So we've talked about the tangent functions in the range. Let's see if we can apply a little bit of this knowledge to a few problems. Suppose that point P is the point on the unit circle obtained by rotating the initial ray through 30 degrees. So theta equals 30 degrees, which is also our reference angle, is 30 degrees, just to remind yourself about the past lessons. And if we remember the diagrams we were looking at in previous lessons, 30, 60, this is 1, square root of 3 over 2, and 1/2. So if we have tangent 30, opposite over adjacent, so I have opposite over adjacent, which is sine over cosine, or y over x. This simplifies to 1 over the square root of 3, which you can't have radicals in the denominator. Let's rationalize them. If I multiply by the square root of 3 over the square root of 3, I get square root of 3 over 3. So there we have tangent 30. Okay, why do we call this function tangent? We explained in one of the first few slides what tangent means. It's a line that touches a circle in just one point. So let's just do a little bit of discovery here. So first of all, let P be the point on the unit circle with center O that is the intersection of the terminal ray after rotation by theta degrees, as shown in the diagram. Let Q be the foot of the perpendicular line from P to the x-axis, and let the line L be the line perpendicular to the x-axis at point 1, 0. So it's touching the unit circle right here at 1, 0. R is the point where the secant line OP intersects line L. I say it's a secant line because if I extend it, it hits the circle at 2 points. So let's show that M equals tan theta. All right, so first of all, segment RS has length M, and side OS adjacent to angle ROS has length 1. I'll show you this on the diagram in a second. So we use tan theta equals opposite over adjacent equals just plain old M. So M equals tan theta. Okay, let's look at that in the diagram. RS has length M. It goes from 0 to M. I mean, we're just naming it a random variable M. OS adjacent to angle ROS. So segment OS has a length of 1 because it goes from 0 to 1. So tangent equals opposite over adjacent, which is M over 1, which is just plain old M. So that's why we call it tangent. Using a segment in the figure, make a conjecture why mathematicians named the function of theta equals sine over cosine the tangent function. Okay, random answers. Maybe because the value of the function, the answer to the question, is the length of the segment that is tangent to the circle. Okay, with our unit circle it works because the length here is 1 because it's a unit circle, and the length here is going to be the length of the segment that's tangent to the circle, right? Okay, hold on a sec. I needed a picture of my figure. Can you use either triangle, POQ or ROS, to calculate the length of M? Well, I mean, they're similar triangles, So because of angle, angle, I've got angle, angle. Because of angle, angle, they are similar triangles. So the sides are proportional. So technically, yes, you can. Okay, letter D. Imagine that you are a mathematician who gets to name the function. How cool would that be? Based upon what you know about the equations of lines, what might you have named the function instead? I mean, if we're doing tangent theta is m over 1, I don't know. This would be our secant line. Joe. I would name it Joe. All right, draw 4 pictures similar to the diagram in exercise 2 to illustrate what happens to the value of tan theta as the rotation of the secant line through the terminal ray increases towards 90 degrees. How does your diagram relate to the work done in exercise 1? Rather than try to decipher my awesome drawings of circles and tangents through the secant line, I copied this from the book so we could just talk about it. The first example, we can see that we have theta, okay, our secant line, and that would be m. So m equals tangent theta, right? Sorry. As theta gets larger, we still have tangent theta as m. So our angle of rotation is getting larger. Our m is getting larger, okay? As the rotation increases to 90 degrees, we aren't quite there yet, but as the rotation increases 90 degrees, the value of m increases by positive infinity. Since m equals tangent theta, the value of tangent theta also increases to positive infinity. So tangent theta approaches infinity. Okay, this is what we did in exercise 1. Just to sort of firm that up a little bit more. But as our theta increases, our m gets bigger and bigger and bigger, approaching infinity. Okay, when the terminal ray is vertical, what is the relationship between secant line OR and tangent line RS? Well, actually, like, as secant line is vertical, I can't do opposite over adjacent. It just doesn't work. So tangent theta is opposite over adjacent. Or let's look at it this way. It's y over x. Well, x is 0 in this case, which that's when the world implodes and we're dividing by 0 and Cookie Monster doesn't have friends and nobody has cookies. We cannot divide by 0, so it just doesn't work. The tangent function is undefined at theta equals 90 degrees, or negative 90. When the terminal ray is horizontal, what is the relationship? Let's see if I can draw that. When the terminal ray is 0, I have tangent theta is y over x. Y is 0, x is 1, so it's 0. So tangent theta is 0 at theta equals 90. Not 96, 90. When the terminal ray is rotated counterclockwise by let's get the right color. By 45 degrees, We are at, what, square root of 2 over 2, square root of 2 over 2, and 1. Tangent theta, or tangent of 45, is square root of 2 over 2. Square root of 2 over 2 equals 1. Cool. All right, number 7, we're going to go through these exercises. Okay, let's look at when theta equals 30. Rotate the initial ray about the origin, the stated number of degrees. Draw a sketch and label the coordinates of point P where the terminal ray intersects the unit circle. What is the slope of the line containing this ray? If you remember, slope is change in y over change in x. So y1 minus y2, and I copied this from the book because, again, my drawing of circles lacks quite often. Sorry. So if we do change in y, which would be 1/2 minus 0, over change in x, which is square root of 3 over 2 minus 0. So we're trying to find the slope of the line containing this ray. So right there, we get 1/2 over square root of 3 over 2, which gives us 1 over the square root of 3, which if I rationalize, multiply by the square root of 3 over the square root of 3, I get square root of 3 over 3. 45 degrees, again I'm doing change in y over change in x. So the y value for 45 degrees is square root of 2 over 2 minus 0. Square root of 2 over 2 minus 0 is the square root of 2 over 2. Divide by the square root of 2 over 2, which is, in fact, 1. And then the 60-degree one. Again, we're calculating slope. Change in y would be square root of 3 over 2 minus 0. Change in x would be 1/2 minus 0. Square root of 3/2 over 1/2 gives me just plain old square root of 3. Awesome. Okay, use the definition of tangent to find tan 30, tan 45, tan 60. How do your answers compare to the works in parts A through C? If I had those same drawings in front of me, which you may have sketched yours, you have them in front of you, I know that tan 30 is opposite over adjacent, which is the square root of, is 1/2 over square root of 3/2, which rationalizes into the square root of 3 over 3. And then tan 45 is opposite over adjacent, which is square root of 2 over 2 over square root of 2 over 2, which rationalizes into 1. Sorry, it doesn't rationalize, it simplifies. And then tan 60 is opposite over adjacent. Square root of 3/2 over 1/2 simplifies to the square root of 3, not 2. If the initial ray is rotated theta degrees about the origin, show that the slope of the line containing the terminal ray is equal to tan theta. So our terminal line, if I draw a circle, unit circle, no matter where it goes, it's always going to intersect the circle at x theta, y theta, which we've said is the same as cosine theta, sine theta. Right? So it's always going to pass through the origin, check. It's always going to pass through the unit circle at that ordered pair. So the slope of the line is always going to be change in y theta minus 0 over x theta minus 0. Oops, that shouldn't be a theta. X theta minus 0, which is y theta over x theta, which is the same as sine theta over cosine theta. Okay, no matter where that is, that's what our slope is going to be. Now that you've shown that the value of the tangent function is equal to the slope of the terminal ray, would you prefer using the name tangent function or slope function? Oh, so I can't use Joe? I guess slope function would have been a better name for it. Why do you think we use tangent instead of slope as the name of the tangent function? Well, if we use the word slope function, I don't know, I think we're using the same terminology or the same vocabulary for two different things. So tangent, we've got tangent to a circle, no matter where it is on that circle. It just makes better sense. So you can have many reasons for this. I'll read what they gave in the curriculum. Answers may vary. Possible reasons include familiarity or comfort with one of the concepts. Tangent is probably used instead of slope due to the historical ideas of trigonometry and geometry. Okay, that'll work. Let's try number 8. Rotate the initial ray about the origin, the stated number of degrees. Draw a sketch and label the coordinates of point P where the terminal ray intersects the unit circle. How does your diagram in this exercise relate to the diagram in corresponding part of exercise 7? What is tan theta for these values of theta? All right, let's look at this first one. I'm going to draw a unit circle. It was really good until that last little part there. 210 degrees means we're going all the way over here. And we have, I need my phi. 210 minus 180 is 30 degrees. So our phi is 30 degrees. So point P is going to be, our x value would be negative root 3 over 2, and our y value is also negative 1/2, right? So tangent of 210 is going to be tan of 30. It's positive, right? Because we're doing y over x, so negative over negative is a positive. And if we do y over x, negative 1/2 over negative root 3 over 2, that simplifies to root 3 over 3 because we have to rationalize our denominator. 225. Draw my unit circle in here. 225 is going to be over here. My terminal ray, point P, let's see, 225 minus 180 is going to be 45 degrees. So tan theta, sorry, my point P here is going to be square root of 2 over 2, comma, square root of 2 over 2. So tan theta is square root of 2 over 2, which is equal to 1. 240 degrees. We're going over here again. Our phi is going to be 60 degrees. So let's see, this point is going to be negative 1/2 as our x value, and negative square root 3, that's a 2, over 2. So tan theta is going to be equal to y over x. So square root of 3. Awesome. What do the results in parts A through C suggest about the value of tangent function after rotating an additional 180 degrees? If the initial ray is rotated by 180 plus theta, then the terminal ray is on the same line as the terminal ray when the initial ray is rotated by theta degrees. Since the slope of the line containing the two terminal rays is the same, I mean, if we're over here, that secant goes all the way through, so the slope of the line is the same. The value of the tangent function for both theta and 180 plus theta is the same. So tangent of theta is equal to tangent of 180 plus theta. It doesn't change. What is the period of the tangent function? 180 degrees, because that it goes back to the beginning. Remember, periodic function is repeatable. It goes so far and then it repeats itself again. For a tangent, our period is 180 degrees because it repeats at that degree, where sine and cosine, it was 360 degrees. Use the results of 7e to explain why tan of 0 is 0. Well, the slope of a horizontal line is in fact 0. And the slope of a vertical line is undefined. Makes perfect sense. Cool, our lesson summary. We don't have to memorize this. We can find it and calculate it. This we have to memorize, but you guys will get it. We know that the range of a tangent function is all real numbers. The period of the tangent function is 180. So the domain goes from 0 to 180. Cool, that was sort of fun.